Hello there, and welcome. Tonight I want to take you somewhere soft and starlit, where you and I can breathe with the sky and listen for a turning we can't quite see. It's late, I know, and perhaps you've been carrying the weight of the day on your shoulders, feeling it pressed down like gravity itself. But here, right now, in this moment we're sharing, I want you to let that weight slowly dissolve, like morning mist meeting the first gentle rays of dawn. Close your eyes if you'd like, or let them rest softly on nothing in particular, and just be here with me as we begin this journey together into one of the cosmos's most intriguing whispers. You see, there's a question that's been drifting through the halls of astronomy, floating between telescopes and equations, settling like stardust in the quiet corners of observatories around the world. It's a question that seems unlikely at first, perhaps even impossible, but the more we sit with it, the more it opens like a door into a room we didn't know existed in our cosmic home. What if the entire universe, this vast expanse of everything we know and everything we don't, is slowly, almost imperceptibly, rotating around an invisible axis? Not spinning wildly like a top, no, but turning with such profound gentleness that it takes the light from the edge of time itself to reveal even the faintest hint of this motion. Before we drift farther into this cosmic mystery, I'd love to know where you're listening from tonight. Are you tucked into bed in a city where the lights compete with the stars? Or perhaps you're in a quiet countryside where the Milky Way still paints its ancient river across your ceiling of night? What time is it there, in your corner of our spinning world? Is it that precious hour when the day releases its hold and tomorrow hasn't yet begun to knock? If this kind of calm wandering through the cosmos feels right to you, if you find yourself drawn to these gentle explorations of the universe's secrets, you might consider subscribing so we can keep meeting under these quiet stars, night after night, question after question, wonder after wonder. A simple like helps others find their way to this peaceful corner of contemplation too, where science meets dreams and questions matter more than answers. Now, let's return to our invisible axis, shall we? When I first encountered this idea, I'll admit, my initial reaction was skepticism wrapped in fascination. How could the entire universe be rotating? What would it even be rotating relative to? These are the kinds of questions that make physicists furrow their brows, and philosophers lean back in their chairs with that particular smile that comes from encountering a truly delicious paradox. And yet, as we'll discover together tonight, there are hints, subtle suggestions written in the oldest light we can see, patterns that whisper of something we're only beginning to understand. Imagine for a moment that you're standing in a vast field at night, far from any city lights, and you slowly turn in a circle, arms outstretched, face tilted toward the stars. As you turn, the whole sky seems to wheel around you, doesn't it? The stars trace their ancient paths, and you might feel, just for a moment, like you're at the center of everything. Now, what if I told you that this feeling, this sense of being part of a grand rotation, might be more accurate than you ever imagined? Not because you're at the center, no, but because you and I and Earth and our Sun and our galaxy and every galaxy we can see might all be participating in a rotation so vast, so slow, so subtle, that it encompasses everything that exists. The universe, as we understand it, began about 13.8 billion years ago in what we call the Big Bang. Though that name doesn't quite capture the profound silence of that first moment. It wasn't an explosion in space. It was the beginning of space itself, time itself, everything itself. And in those first impossibly brief moments, the universe was smaller than an atom, hotter than anything we can imagine, and perfectly, almost perfectly uniform. Almost. Those tiny imperfections, those minute variations in density and temperature, would eventually become the seeds of galaxies, stars, planets, and ultimately us. But what if, in addition to these tiny ripples that would become the large-scale structure of the cosmos, there was something else? What if there was a preferred direction, a cosmic axis, established in those first moments that has been gently guiding the universe's evolution ever since? This isn't a new idea exactly, but it's one that has gained intriguing support from unexpected quarters in recent years. You see, when we look at the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills every cubic centimetre of space, we expect to see randomness. We expect the tiny temperature variations to be distributed evenly in all directions, with no preferred orientation, no special axis. The universe, according to our standard models, shouldn't have a direction. It should be what we call isotropic, the same in all directions, like a perfectly smooth sphere. But what if it isn't? What if there's a subtle anisotropy, a gentle preference for one direction over another that we're only now beginning to detect with our most sensitive instruments? The story begins, as many cosmic stories do, with light. Not just any light, but the oldest light in the universe, the cosmic microwave background, or CMB. This light has been travelling for over 13 billion years to reach us, carrying with it information about the universe when it was only 380,000 years old, a mere infant in cosmic terms. When the universe was that young, it was filled with a hot, dense plasma of particles that light couldn't penetrate. But then, as the universe expanded and cooled, atoms formed for the first time, and suddenly light was free to travel. That first light, that cosmic dawn, is what we see today as the CMB, cooled by the universe's expansion from a brilliant glow to a faint microwave whisper. Now, here's where our story takes an interesting turn. When scientists first started making detailed maps of the CMB, they expected to find random variations, and they did. But they also found something else, something unexpected and to this day not fully explained. They found what appeared to be large-scale alignments in the CMB, patterns that seemed to pick out a special direction in space. Some scientists call it the axis of evil, though I prefer to think of it as the axis of intrigue, or perhaps the cosmic mystery axis. The name axis of evil was actually coined somewhat tongue-in-cheek by cosmologist Juan, reflecting the frustration and fascination that this unexpected finding provoked in the scientific community. Picture this. You're looking at a map of the entire sky, showing the temperature of the CMB in every direction. The variations are tiny, only about 1 part in 100,000, but they're there, and they tell us about the seeds of structure in the early universe. Now, if the universe is truly isotropic, these variations should be random. There should be no preferred direction, no special axis. But when scientists analyze the larger scale patterns in the CMB, particularly what we call the quadrupole and octopole moments, think of these as the biggest, most fundamental patterns in the temperature map, they find that these patterns seem to be aligned with each other, and possibly with other cosmic structures as well. It's as if the universe is saying, very quietly, look this way, there's something special about this direction. But what could be special about any particular direction in space? If the universe began from a single point and expanded uniformly in all directions, why would one direction be different from any other? These are the questions that keep cosmologists up at night, though perhaps tonight they'll help you drift off to sleep instead, wrapped in the comfort of cosmic mystery. Let me paint you a picture of what this might mean. Imagine the universe as an enormous balloon, expanding as we blow air into it. In the standard picture, the balloon expands uniformly, with no preferred direction. Every point on the balloon's surface is equivalent to every other point. But what if the balloon is slightly oval instead of perfectly round? What if it's expanding just a tiny bit faster in one direction than in others? Or what if the balloon itself is slowly rotating as it expands? These are simplified analogies, of course, but they help us visualize what an anisotropic universe might be like. The evidence for this cosmic axis doesn't come from just one observation or one team of scientists. It's been building slowly, quietly, like snow accumulating on a winter night. The WMAP, satellite which mapped the CMB in exquisite detail from 2001 to 2010, first revealed these large-scale alignments. When the Planck satellite, an even more sensitive instrument, confirmed many of these findings, the mystery deepened. It wasn't just an instrumental error or a fluke of one particular observation. Something real seemed to be happening. But science is cautious, as it should be. Extraordinary claims require extraordinary evidence, and the claim that the universe has a preferred direction is certainly extraordinary. So scientists have been working to rule out more mundane explanations. Could it be contamination from our own galaxy? Could it be an artifact of how we analyze the data? Could it be just a statistical fluke, one of those rare coincidences that happen even in a random universe? These are all possibilities that have been and continue to be investigated. Yet the hints keep accumulating. It's not just the CMB. When astronomers look at the distribution of galaxies across the sky, Some studies suggest there might be more galaxies in one direction than another, though this is still debated. When they examine the polarization of light from distant quasars, some analyses find alignments that shouldn't be there if the universe is isotropic. It's as if we're seeing the same message written in different languages across the cosmos. There might be something special about a particular direction in space. Now you might be wondering, what direction are we talking about? Where does this mysterious axis point? The answer, intriguingly, seems to be in the direction of the constellation Virgo, though the exact orientation depends on which feature you're looking at and how you analyze the data. Some researchers have noted that this direction is suspiciously close to the ecliptic plane, the plane in which Earth orbits the Sun, which has led to suggestions that the whole thing might be a systematic error related to our motion through space, but others argue that the alignments persist even when our motion is accounted for. Let's pause here for a moment and consider what we're really talking about. We're not suggesting that the universe is spinning like a record on a turntable. The rotation, if it exists, would be incredibly slow, so slow that it would take billions of years for even a tiny fraction of a complete turn. We're talking about something subtle, something that might manifest only in the largest structures and the oldest light, something that requires the entire observable universe as our laboratory to detect. And perhaps that's what makes this mystery so compelling. It reminds us that despite all our knowledge, despite our powerful telescopes and sophisticated theories, the universe still holds secrets. It still has the capacity to surprise us, to challenge our assumptions, to invite us into deeper contemplation of what reality really is. In a way, the possibility of a cosmic axis is a reminder of our place in the grand scheme of things. We're not outside observers studying the universe, we're part of it, embedded in it, rotating with it if indeed it rotates. Think about your own life for a moment. You wake up each morning as Earth completes another rotation on its axis. You move through the seasons as Earth orbits the Sun. Your solar system drifts around the center of the Milky Way galaxy, completing one grand orbit every 250 million years or so. Our galaxy itself is moving, drawn by gravity toward the great attractor and beyond. And now, perhaps, all of this motion is part of an even grander rotation, a turning of the universe itself around an axis we're only beginning to perceive. There's something deeply peaceful about this idea, isn't there? All this motion, all this turning, and yet we feel stillness. We lie in our beds at night, seemingly motionless, while participating in a cosmic dance of unimaginable scope. It's like being a child again, lying on the grass, feeling the earth solid beneath you while knowing, in some deep part of your mind, that you're actually spinning through space at tremendous speed. The contradiction between what we feel and what we know creates a kind of vertigo, but also a sense of wonder. As we continue our journey tonight, we'll explore the evidence for this cosmic axis in more detail. We'll look at what scientists have discovered and what they're still puzzling over. We'll consider different theories about what could cause such an axis to exist, and we'll contemplate what it might mean for our understanding of the universe and our place in it. But for now, let's just sit with the possibility. Let it settle into our consciousness like a new constellation we're just learning to see. You know, there's something beautiful about questions that don't have easy answers. In our daily lives, we're often pressed for certainty, for definitive solutions, for clear-cut responses. But here, in the realm of cosmology, we can luxuriate in uncertainty. We can say, perhaps, and maybe, and what if, without apology. We can follow ideas down winding paths that might lead nowhere or might lead to profound revelations. We can be explorers in the truest sense, venturing into unknown territory with nothing but our curiosity as a compass. The question of whether the universe rotates around an invisible axis is one of these beautiful uncertainties. It sits at the intersection of observation and theory, of what we can measure and what we can imagine. It challenges some of our most fundamental assumptions about the cosmos while potentially confirming others. It's a question that connects the largest scales we can observe with the fundamental laws of physics that govern the smallest particles. In a sense, it's a question about everything. And here's a thought that might accompany you as you drift towards sleep tonight. If the universe does have a preferred axis, if it is slowly rotating in some higher dimensional sense we don't fully understand, then every atom in your body knows this direction. Every particle that makes up your being is aligned with this cosmic axis, has been since the beginning of time, and will be until time itself ends. You're not just in the universe, you're of it, woven into its very fabric, turning with its great slow turning. We begin our exploration proper by considering the scales and spins we already know, the rotations within rotations that define our cosmic neighbourhood. You see, rotation is everywhere in the universe. It's one of the most fundamental types of motion, arising naturally whenever there's a bit of asymmetry, a slight push or pull that sets things turning. From the smallest dust devils on Earth to the grandest spiral galaxies, rotation is a universal theme, a cosmic motif repeated at every scale. Let's start close to home, with the rotation you know most intimately, Earth's daily spin on its axis. Every 24 hours, our planet completes one full rotation, carrying us from day into night and back to day again. This rotation isn't just a curiosity, it's fundamental to life as we know it. It creates the cycle of light and darkness that governs the rhythms of almost every living thing. It generates the Coriolis effect that shapes our weather patterns and ocean currents. It even affects the shape of Earth itself, causing our planet to bulge slightly at the equator. But here's something you might not have considered. Earth's rotation is slowing down. The Moon's gravitational pull creates tides, and the friction of these tides against the ocean floor and shorelines gradually transfers angular momentum from Earth to the Moon. Every century our days get about 1.8 milliseconds longer. It's an imperceptible change on human timescales, but over billions of years it adds up. When Earth first formed, a day was only about 6 hours long. In the distant future, if nothing else intervenes, Earth will become tidally locked to the Moon, always showing the same face to our celestial companion, and a day will last as long as a month. This slowing of Earth's rotation is a reminder that nothing in the universe spins in isolation. Every rotation affects and is affected by everything around it. The Moon, which is slowly stealing Earth's rotational energy, is itself moving away from us at about 3.8 centimeters per year, about the same rate your fingernails grow. This cosmic dance, this gradual exchange of angular momentum, has been going on for billions of years and will continue for billions more. Now let's zoom out a bit and consider Earth's orbit around the Sun. This too is a rotation, though we usually call it a revolution to distinguish it from Earth's spin on its axis. Our planet traces an elliptical path around our star, completing one orbit every 365.25 days. This orbital motion, combined with the tilt of Earth's axis, gives us our seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer while the southern hemisphere experiences winter, and vice versa. But Earth's orbit isn't as simple as it might seem. Our planet's path around the Sun is affected by the gravitational pull of all the other planets, especially Jupiter, the giant of our solar system. These perturbations cause Earth's orbit to change slowly over time. The shape of the orbit becomes more or less elliptical in cycles lasting about 100,000 years. The tilt of Earth's axis varies between 22.1 and 24.5 degrees over a period of about 41,000 years, and the direction Earth's axis points processes, or wobbles, like a spinning top, completing one full wobble every 26,000 years. These cycles, known collectively as Milankovitch cycles after the Serbian scientist who first calculated them, have profound effects on Earth's climate. They're responsible for the ice ages that have periodically gripped our planet over the past few million years. When the cycles align to reduce the amount of sunlight reaching the northern hemisphere in summer, ice sheets can grow and spread, plunging the planet into a glacial period. When they align to increase summer sunlight, the ice retreats, and we enter an interglacial period like the one we're in now. Think about that for a moment. The slow wobbles and shifts in Earth's rotation and orbit, changes so gradual that they're imperceptible on human timescales, can transform the entire planet. They can bury continents under miles of ice, or turn them into lush green paradises. They remind us that we live in a dynamic universe, where everything is in motion, everything is changing, even if that change is too slow for us to perceive directly. Now let's expand our view further and consider the rotation of our entire solar system. The Sun and all its planets formed from a rotating cloud of gas and dust about 4.6 billion years ago. As this cloud collapsed under its own gravity, it spun faster, like a figure skater pulling in their arms. This rotation flattened the cloud into a disk, which is why all the planets orbit in roughly the same plane and in the same direction. It's also why most planets rotate in the same direction they orbit. though there are interesting exceptions like Venus, which rotates backward, and Uranus, which is tilted so far that it essentially rolls along its orbit. The Sun itself rotates, completing one turn about every 27 days at its equator. But because the Sun is not a solid body but a ball of plasma, different parts rotate at different rates. The equator rotates faster than the poles, a phenomenon called differential rotation. This differential rotation twists and tangles the Sun's magnetic field, leading to the formation of sunspots and the eruption of solar flares. The Sun's rotation, in other words, drives the solar activity that can affect satellites, power grids, and even the northern and southern lights here on Earth. Our solar system as a whole is also in motion, orbiting, around the centre of the Milky Way galaxy. This galactic orbit is vast, almost beyond comprehension. The Sun and its planets are located about 26,000 light-years from the galactic centre, in a relatively quiet neighbourhood between two of the galaxy's spiral arms. We're orbiting at a speed of about 230 kilometers per second, which sounds fast until you realise that even at this speed, it takes us about 250 million years to complete one orbit. The last time our solar system was in this position in the galaxy, dinosaurs were just beginning to emerge on Earth. As we orbit the galactic centre, we also bob up and down through the galactic plane, like horses on a cosmic carousel. This oscillation takes about 70 million years to complete, and some scientists have suggested it might be linked to mass extinction events on Earth. The idea is that as we pass through the denser parts of the galactic disk, we're more likely to encounter cosmic hazards like asteroids or comets knocked from their orbits, though this remains a topic of debate. The Milky Way itself is rotating, but not like a solid disk. Stars closer to the centre orbit faster than those farther out, but not in the simple way you might expect from Kepler's laws. This is one of the observations that led to the discovery of dark matter. The stars in the outer parts of the galaxy are orbiting too fast for the amount of visible matter we can see. There must be something else there, something invisible, providing additional gravitational pull. This dark matter, whatever it is, makes up about 85% of all the matter in the universe, and we still don't know what it is. Our galaxy's rotation has shaped its beautiful spiral structure. The spiral arms are not permanent features, but rather density waves, regions where stars and gas clouds bunch up as they orbit. It's like a cosmic traffic jam that maintains its shape even as individual cars, or in this case stars, move through it. New stars are born in these dense regions, lighting up the spiral arms and giving galaxies their characteristic pinwheel appearance. But the Milky Way's rotation is even more complex than this. Recent observations have revealed that our galaxy's disk is warped, like a vinyl record left in the Sun. One end of the galaxy curves up while the other curves down. This warp might be caused by the gravitational influence of our satellite galaxies, the Large and Small Magellanic Clouds, or it might be a remnant from an ancient collision with another galaxy. The galaxy also has a bar-shaped structure at its centre, which rotates at a different rate than the spiral arms, adding another layer of complexity to the galactic dance. And our galaxy doesn't rotate in isolation. The Milky Way is part of a group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. These galaxies orbit around their common centre of mass, drawn together by gravity. The Milky Way and Andromeda are on a collision course, approaching each other at about 110 kilometers per second. Don't worry though, the collision won't happen for another 4 billion years, and when it does, the vast distances between stars mean that individual stellar collisions will be extremely rare. The Local Group itself is part of a larger structure called the Virgo supercluster, which contains thousands of galaxies arranged in a complex web of filaments and voids. And the Virgo supercluster is just one lobe of an even larger structure called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains about 100,000 galaxies spread across 520 million light-years. All these galaxies are moving, flowing like a cosmic river toward a region called the Great Attractor, a gravitational anomaly whose exact nature remains mysterious. When we map the motions of galaxies on these vast scales, we find that they're not just expanding away from each other due to the expansion of space itself. They also have peculiar velocities, motions through space caused by gravitational attractions. These motions form a complex pattern of cosmic flows, with galaxies streaming along invisible gravitational highways toward massive concentrations of matter. Now, here's where our story takes an interesting turn. If you compressed the entire age of the cosmos into a single day, with the Big Bang occurring at midnight, the first stars would light up around 1 Gua am. Galaxies would begin forming by 2 Gua am. Our solar system wouldn't appear until about 3:40 p.m. Life on Earth would emerge around 5 Gua p.m. Dinosaurs would rule from about 10:50 p.m. until 11:40 p.m. And all of human history, from the first Homo sapiens to now, would occupy only the last 14 seconds before midnight. In this compressed cosmic day, rotations would be happening at every scale and every moment. The universe would be alive with spinning, from the quantum spin of subatomic particles to the grand rotation of galaxy clusters. And perhaps, just perhaps, the entire universe itself would be participating in a rotation so slow, so vast, that it would be barely perceptible even across the entire 24-hour cosmic day. This brings us back to our central question. Could the universe as a whole be rotating? To understand what this might mean, we need to think carefully about what we mean by rotation. In our everyday experience, rotation means turning around an axis. A wheel rotates around its axle. Earth rotates around its axis. But what would it mean for the universe to rotate? What would it be rotating relative to? What would define its axis? These are profound questions that touch on the nature of space and time themselves. In Einstein's general relativity, which is our best theory of gravity and the large-scale structure of the universe, space and time are not fixed stages on which cosmic events play out. They're dynamic, flexible, capable of being curved and twisted by matter and energy. In this framework, a rotating universe is possible, at least in principle. It would be a universe where space-time itself has a kind of twist or curl to it, a built-in preference for rotation that would affect everything within it. One of the first scientists to seriously consider the possibility of a rotating universe was the mathematician Kurt Gödel, famous for his incompleteness theorems in logic. In 1949, Gödel found a solution to Einstein's equations that described a rotating universe. In Gödel's universe, the rotation would create closed time-like curves, paths through space-time that loop back on themselves. In principle, this would allow for time travel into the past, though there are good reasons to believe our actual universe doesn't have this property. Since Gödel's work, cosmologists have found other theoretical models of rotating universes. Some of these are variations on the standard Big Bang model where the universe has a small amount of rotation from the very beginning. Others involve more exotic scenarios, like universes with extra dimensions or unusual topologies. But all of them share the feature that rotation is a global property of the universe, not just something that happens within the universe, but something that characterizes the universe as a whole. Observationally, detecting universal rotation is extremely challenging. We can't step outside the universe to see if it's spinning. We can only look for subtle signs in the light that reaches us from distant sources. One possibility is that a rotating universe would cause light from distant galaxies to be polarized in a particular pattern. Another is that it would create temperature variations in the cosmic microwave background that have a special spiral pattern. Still another is that it would cause more galaxies to rotate in one direction than the other. Some of these signatures have been looked for, and intriguingly, there have been claims of detection, though none are universally accepted. For example, some studies have suggested that spiral galaxies in one part of the sky are more likely to be rotating clockwise as seen from Earth, while those in the opposite part of the sky are more likely to be rotating counterclockwise. This would be expected if the universe as a whole were rotating, but other studies have failed to confirm this effect and the debate continues. The question of universal rotation is tied to one of the deepest principles in cosmology, the Copernican principle. This is the idea that we don't occupy a special place in the universe. Earth is not at the center of the solar system. The Sun is not at the center of the galaxy. Our galaxy is not at the center of the universe. And extending this principle, there should be no special direction in the universe, no preferred axis that would distinguish one direction from another. But what if the Copernican principle, at least in its strongest form, is wrong? What if there is something special about our location, or about a particular direction in space? This wouldn't mean going back to the pre-Copernican view that Earth is at the center of everything. But it might mean that the universe is not as uniform and isotropic as we've assumed. It might have a richer, more complex structure than our simplest models suggest. The idea that the universe might have a preferred direction is not as radical as it might seem. We already know that the universe is not perfectly uniform. There are galaxies and clusters of galaxies, vast cosmic voids, and great walls of matter stretching across hundreds of millions of light years. These structures formed from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. If such small initial fluctuations can lead to such dramatic structures, why not a small initial rotation leading to a universal preferred direction? Moreover, we know that the observable universe, the part of the universe we can see, is finite. It extends about 46 billion light-years in every direction from us. Beyond that is more universe, possibly infinitely more, that we cannot see because light from those regions hasn't had time to reach us since the Big Bang. The observable universe is like our cosmic horizon, and just as Earth's horizon doesn't mean the world ends there, the cosmic horizon doesn't mean the universe ends there. Now, if the observable universe is finite, it's not so strange to think it might have some overall properties like rotation that wouldn't make sense for an infinite universe. It's a bit like how a hurricane can have overall rotation even though it's made up of countless air molecules moving in complex patterns. The rotation emerges from the collective behavior of all the parts, even though no single part is aware of the overall pattern. There's another way to think about this. In quantum mechanics, particles can have a property called spin, which is a kind of intrinsic angular momentum. An electron, for example, can be spin up or spin down, and this property affects how it behaves in magnetic fields and how it interacts with other particles. Now, we don't usually think of the universe as a quantum object, but some theories of quantum gravity suggest that at the very smallest scales, space and time themselves might have quantum properties. Could the universe as a whole have something like a quantum spin? It's a speculative idea, but not an impossible one. As we contemplate these possibilities, it's worth remembering that we're part of this potentially rotating universe. Every atom in our bodies, every thought in our minds, every breath we take is embedded in this cosmic dance. If the universe is rotating, we're rotating with it, carried along like leaves on a slowly spinning pond. We can't feel this motion any more than we can feel Earth's orbit around the Sun, but it would be shaping our reality in subtle ways we're only beginning to understand. The search for universal rotation is part of a larger quest to understand the initial conditions of the universe. Why did the universe begin in the particular state it did? Why do the laws of physics have the particular form they have? Why does the universe exist at all? These are questions that push the boundaries of science and philosophy, questions that may not have answers within the framework of science, as we currently understand it. Some physicists have proposed that our universe is just one of many in a vast multiverse, each with different properties, different laws of physics, perhaps different amounts of rotation. In this view, we find ourselves in a universe with the properties we observe not because these properties are special, but because they're compatible with our existence. Universes with very different properties might exist but wouldn't have observers to notice them. Others suggest that the initial conditions of the universe might be determined by some deeper principle we haven't discovered yet, a kind of cosmic DNA that encodes the blueprint for everything that follows. Perhaps rotation, or the lack thereof, is part of this cosmic genetic code, set at the moment of the Big Bang or even before, in some pre-Big Bang epoch we can barely imagine. As we delve deeper into the mystery of cosmic rotation, we encounter a fascinating paradox. The more we learn about the universe, the more we realize how much we don't know. Every answer leads to new questions. Every discovery opens new mysteries. It's like climbing a mountain only to discover that what you thought was the peak is just a foothill, with higher peaks stretching beyond, shrouded in clouds. This might seem frustrating, but I find it deeply comforting. It means the universe will never run out of surprises. There will always be new wonders to discover, new questions to ponder, new mysteries to explore. The possibility that the universe might be rotating around an invisible axis is just one of these mysteries, but it's one that touches on some of the deepest questions we can ask about the nature of reality. Consider this. If the universe is rotating, even infinitesimally slowly, then it has angular momentum. Angular momentum is conserved, meaning it can't be created or destroyed, only transferred from one form to another. So where did this angular momentum come from? Was it present at the Big Bang? Did it arise from some process in the very early universe? Or is it a remnant from whatever came before the Big Bang, a fossil from a previous cosmic epoch? These questions lead us into deep waters indeed. They force us to confront the limits of our knowledge and the boundaries of science itself. But they also remind us of the incredible journey of discovery we're on. Just a century ago, we didn't even know there were galaxies beyond our own. Now we're contemplating the rotation of the entire observable universe. Who knows? What wonders await us in the next century or the next millennium? As you lie there tonight, perhaps feeling the gentle pull of sleep beginning to take hold, think about all these nested rotations we've explored. Earth spinning on its axis, orbiting the Sun, which orbits the galactic center, which moves through the local group, which flows through the cosmic web. And perhaps, encompassing all of this, the universe itself slowly turning around an axis we can barely perceive. There's a beautiful symmetry to this idea, isn't it? From the smallest scales to the largest, from electrons spinning around atomic nuclei to galaxies spinning in the cosmic void, rotation is everywhere. It's as if the universe has a fundamental preference for this type of motion, a deep affinity for the curve rather than the straight line, for the cycle rather than the arrow. Now imagine that invisible axis we've been discussing, stretching across the cosmos like an infinite spindle around which everything turns. It wouldn't be a physical object, of course, but rather a geometric property of space-time itself, a direction picked out by the universe's rotation. If you could somehow see this axis, it might appear as a line of special significance, a cosmic meridian dividing the universe into two complementary halves. But here's the truly mind-bending part. Because we're inside the universe, rotating with it. If it rotates, we can never directly perceive this rotation. It's like trying to detect the motion of a train by looking at the other passengers. Everyone is moving together, so there's no relative motion to observe. We can only detect the universe's rotation by looking for subtle asymmetries, tiny deviations from perfect uniformity that might reveal the universe's hidden spin. This search for cosmic rotation is emblematic of modern cosmology's greatest challenges. We're trying to understand something vastly larger than ourselves, something we're embedded within and can never see from the outside. It's like a fish trying to understand the ocean, or a cell trying to understand the body it's part of. We have to be clever, using indirect observations and sophisticated mathematics to piece together a picture of the whole from our limited vantage point. The possibility of universal rotation also raises profound questions about the nature of time. In our everyday experience, time seems to flow uniformly from past to future. But in general relativity, time is more flexible. It can be stretched and compressed by gravity, and in a rotating universe it could be twisted as well. This doesn't mean time travel becomes possible, necessarily, but it does mean that time might have a more complex structure than we usually imagine. Think about how rotation affects time on Earth. Because our planet is rotating, clocks at the equator are moving faster through space than clocks at the poles. According to special relativity, this means time passes slightly more slowly at the equator. The effect is tiny, only about 10 nanoseconds per day, but it's real and has been measured. GPS satellites have to account for this effect to maintain their accuracy. Now scale this up to the entire universe. If the universe is rotating, different regions might experience time at slightly different rates, depending on their position relative to the axis of rotation. Over cosmic timescales, these tiny differences could add up, potentially affecting the evolution of galaxies, the formation of structures, even the development of life. This brings us to one of the most profound aspects of the rotating universe hypothesis. It would mean that location matters on a cosmic scale, not in the sense that one place is more important than another, but in the sense that different locations would have subtly different relationships to the cosmic axis. It would be as if the universe had a grain, like wood, with properties that vary slightly depending on whether you're aligned with or against this grain. For us, living our brief lives on a small planet orbiting an ordinary star, these cosmic considerations might seem abstract and distant. But they're part of the grand context in which our lives unfold. Every moment of consciousness, every act of love or creativity, every dream and every breath takes place within this possibly rotating cosmos. We're not separate from these vast cosmic processes, we're expressions of them, temporary patterns in the great turning of space and time. As we prepare to delve deeper into the evidence for cosmic rotation, let's pause to appreciate the audacity of what we're attempting. We're trying to determine whether the entire universe is rotating by analysing light that's travelled for billions of years, by studying the orientations of galaxies so distant they appear as mere smudges in our most powerful telescopes, by detecting variations in temperature so small they're measured in millionths of a degree. It's a testament to human ingenuity and curiosity that we can even ask these questions, let alone begin to answer them. Our ancestors looked up at the night sky and saw gods and heroes, bears and hunters. We look up and see a vast cosmic laboratory where we can test our theories about the fundamental nature of reality. Both views inspire awe, but ours comes with the added thrill of discovery, the possibility that we might actually figure out how it all works. Yet even as we celebrate our scientific achievements, we should remain humble. The universe has surprised us before and will surely surprise us again. The discovery of dark matter and dark energy reminded us that most of the universe is made of stuff we don't understand. The discovery of exoplanets showed us that planetary systems can be far more diverse than we imagined. And if the universe is indeed rotating, it would be another reminder that our cosmic home is stranger and more wonderful than we knew. The story of cosmic rotation is still being written. New observations from more powerful telescopes, new analyses of existing data, new theoretical insights, all of these could change our understanding in the coming years. Perhaps we'll find definitive evidence that the universe is rotating, or perhaps we'll rule it out entirely. Or perhaps, as often happens in science, we'll find that the truth is more subtle and more interesting than either simple possibility. But regardless of what we ultimately discover, the journey of exploration is valuable in itself. It stretches our minds, challenges our assumptions, and reminds us of our place in the grand scheme of things. It connects us to the cosmos in a deep and meaningful way, showing us that we're not just in the universe but of it, participants in a cosmic story that began billions of years ago and will continue for billions of years to come. As we move forward in our exploration tonight, we'll examine the specific evidence that has led some scientists to propose that the universe might be rotating. We'll look at the cosmic microwave background in more detail, exploring those mysterious alignments that have puzzled cosmologists for 2 decades. We'll consider alternative explanations and the ongoing debates within the scientific community, and we'll ponder what it all means for our understanding of the cosmos and our place within it. The night is still young in cosmic terms, and our journey has just begun. There are mysteries to explore, wonders to contemplate, and perhaps, if we're lucky, a few answers to uncover. So settle in, let your mind wander among the stars, and let's continue our exploration of one of the universe's most intriguing possibilities. That everything we know, everything we see, everything we are, is part of a vast, slow cosmic rotation around an invisible axis that stretches from one end of existence to the other. The universe, in all its vastness, continues to turn, or perhaps it doesn't, and we, small as we are, have the remarkable privilege of wondering which is true. In that wondering, in that questioning, we touch something infinite, something that connects us to the cosmos in ways we're only beginning to understand. And perhaps that connection, that sense of being part of something immeasurably vast and beautiful, is what this journey is really about. Now, let's turn our attention to the mystery itself, to the subtle clues written in ancient light that suggest our universe might be more than we imagined. Consider this. When you look at the night sky, you're seeing the past. The light from the nearest star took over 4 years to reach your eyes. The light from the Andromeda galaxy travelled for 2.5 million years. And the cosmic microwave background, that faint glow that fills all of space, has been travelling for over 13 billion years, carrying with it secrets from the universe's infancy. It's in this ancient light that we search for signs of cosmic rotation, like detectives examining evidence from a crime scene that's billions of years old and billions of light years away. The clues are subtle, ambiguous, open to interpretation, but they're there, waiting to be understood, waiting to tell us whether our universe spins through dimensions we can barely imagine. The story of these discoveries begins in the 1960s, when 2 radio astronomers named Arno Penzias and Robert Wilson were trying to eliminate noise from a sensitive microwave antenna. They found a persistent hiss that seemed to come from every direction in the sky. At first, they thought it might be interference from New York City, or even pigeon droppings in their antenna. But after eliminating every possible source of contamination, they realized they had discovered something profound: the afterglow of the Big Bang itself. This cosmic microwave background radiation was predicted by theorists who had worked out that the early universe must have been hot and dense, and that as it expanded and cooled, it would have left behind a faint thermal radiation filling all of space. The discovery of the CMB was a triumph for the Big Bang theory, and earned Penzias and Wilson the Nobel Prize in Physics. But the CMB held more secrets than anyone initially realized. It wasn't perfectly uniform. There were tiny variations in temperature, regions slightly hotter or colder than average by just a few parts in 100,000. These variations were the seeds of all cosmic structure, the tiny density fluctuations that would eventually grow into galaxies, stars, and planets. Mapping these variations became one of the most important tasks in cosmology, a way to read the universe's baby picture and understand how it grew into the cosmos we see today. The first detailed map of the CMB came from the COBE satellite, launched in 1989. COBE confirmed that the CMB had exactly the spectrum expected from a perfect thermal source, and it detected those crucial temperature variations for the first time. The map it produced looked like an oval projection of the entire sky, painted in false colours to show the tiny temperature differences. Blue regions were slightly cooler than average, red regions slightly warmer. When cosmologists analysed COBE's map, they expected to find random variations with no preferred direction or orientation, and on small scales that's exactly what they found. But when they looked at the larger scales, at the biggest patterns in the temperature variations, they noticed something odd. The patterns seemed to have preferred orientations, alignments that shouldn't exist if the universe is truly isotropic. At first, many scientists assumed this was a fluke or an artifact of COBE's limited resolution. But when the WMAP satellite produced much more detailed maps of the CMB in the 2000s, the alignments were still there. Even more troubling or exciting depending on your perspective, WMAP found additional anomalies. There was a cold spot in the CMB larger than expected. There was less variation in temperature on large scales than predicted, and those mysterious alignments, particularly in what cosmologists call the quadrupole and octopole moments, seemed even more pronounced. The quadrupole moment is essentially the larger scale pattern in the CMB, aside from the overall average temperature. Think of it as the biggest possible temperature variation you could have across the sky. The octopole is the next level of complexity. In a perfectly isotropic universe, these patterns should be randomly oriented. But in the observed CMB, they seem to be aligned with each other, and possibly with other cosmic structures. Some cosmologists dubbed this alignment the axis of evil, a name that reflects both frustration and fascination. It's evil because it challenges our standard cosmological models, but it's also intriguing because it might be telling us something profound about the universe. The axis seems to point roughly toward the constellation Virgo, though the exact direction depends on how you analyse the data. When the Planck satellite, launched in 2009, provided even more precise measurements of the CMB, many hoped it would resolve the mystery. Either the alignments would disappear, revealed as statistical flukes or systematic errors, or they would be confirmed beyond doubt. But Planck did neither. It confirmed many of the anomalies found by WMAP, including the alignments, but it also raised new questions. The evidence was stronger in some ways, weaker in others. The mystery deepened. So what could cause these alignments? One possibility is that the universe is indeed rotating, or was rotating in its early history. A rotating universe would naturally create preferred directions in the CMB. The rotation would leave its fingerprint in the ancient light, a subtle twist or curl that we're detecting billions of years later. It's as if the universe is a vast vinyl record, and we're trying to determine if it's spinning by analysing the pattern of grooves. But rotation isn't the only possible explanation. The alignments could be caused by a universe that's expanding at different rates in different directions, what cosmologists call a Bianchi universe, after the Italian mathematician who first studied such models. Or they could be due to the topology of space itself. Perhaps the universe isn't simply connected but has a more complex shape, like a torus or a Klein bottle, that creates preferred directions. Another possibility is that we're seeing the effect of structures beyond our observable universe. Remember, we can only see a finite portion of what might be an infinite cosmos. Perhaps there are massive structures beyond our cosmic horizon whose gravitational pull is affecting what we observe, creating the illusion of preferred directions. It would be like trying to understand ocean currents by observing only a small patch of water, not realizing The distant continents are shaping the flow, or perhaps the anomalies are telling us that our standard model of cosmology needs modification. The model assumes that the universe is homogeneous and isotropic on large scales, that the laws of physics are the same everywhere, that dark matter and dark energy have particular properties. If any of these assumptions are wrong, it could manifest as unexpected patterns in the CMB. There's also the sobering possibility that the alignments are indeed just statistical flukes or systematic errors that we haven't properly accounted for. The CMB has been travelling through space for over 13 billion years. Along the way, it's been affected by all the matter it's passed through, a phenomenon called the integrated Sachs-Wolf effect. It's been gravitationally lensed by massive structures. Our own motion through space creates a dipole pattern that has to be carefully subtracted. Our galaxy emits radiation that can contaminate the signal. Perhaps when all these effects are properly accounted for, the anomalies will disappear. But many cosmologists find this explanation unsatisfying. The alignments have persisted through 3 generations of increasingly sophisticated satellites. They've been analysed by multiple independent teams using different methods. They appear not just in temperature maps, but also in polarization data. If they're errors, they're remarkably persistent ones. The search for evidence of cosmic rotation extends beyond the CMB. Astronomers have looked for rotation in the distribution of galaxies themselves. If the universe is rotating, you might expect to see more galaxies rotating in one direction than another, depending on where you look in the sky. Some studies have claimed to find such an effect, reporting an excess of left-handed spiral galaxies in one part of the sky and right-handed spirals in another. But other studies have found no such asymmetry, and the debate continues. There's also the question of quasar polarization. Quasars are extremely bright objects powered by supermassive black holes in distant galaxies. The light from quasars is often polarized, and some studies have found that this polarization seems to be aligned over vast distances, far larger than expected if orientations were random. This could be another sign of a universal preferred direction, though again, the evidence is controversial. Recently, astronomers have been investigating something called cosmic birefringence. This is a phenomenon where the polarization of light rotates as it travels through space. It's predicted by some theories of physics beyond the standard model, particularly those involving axion-like particles. Some analyses of CMB polarization data have found hints of cosmic birefringence, which could be related to universal rotation, though the connection is indirect and theoretical. As we contemplate all this evidence, it's worth remembering that we're dealing with some of the most difficult measurements ever attempted. We're trying to detect patterns in radiation that's incredibly faint, that's been travelling through space for most of the age of the universe, that's been affected by countless intervening structures. We're pushing our instruments and our analysis techniques to their absolute limits. It's no wonder that the results are ambiguous and controversial, but that's part of what makes this mystery so fascinating. We're on the edge of knowledge, peering into the unknown, trying to discern whether the shadows we see are real features or tricks of the light. It's science at its most fundamental, where observation meets theory, where data confronts expectation, where the universe might be trying to tell us something we don't yet know how to hear. The possibility that the universe is rotating around an invisible axis challenges us to think about space and time in new ways. If confirmed, it would be one of the most profound discoveries in cosmology, fundamentally changing our picture of the cosmos. It would mean that the universe has a kind of handedness, a built-in directionality that affects everything within it. It would raise deep questions about why the universe has this property and what it means for the laws of physics. Even if the universe isn't rotating, the search for rotation is valuable. It's forced cosmologists to scrutinize their data more carefully, to develop new analysis techniques, to question their assumptions. It's led to improved measurements of the CMB and better understanding of systematic errors. It's inspired new theoretical work on alternative cosmological models. In science, even wrong ideas can lead to progress if they're wrong in interesting ways. As you drift towards sleep tonight, perhaps you can imagine yourself as a cosmic detective, sifting through clues billions of years old, trying to solve one of the universe's greatest mysteries. The evidence is spread across the entire sky, written in the faint glow of ancient light, encoded in the spin of distant galaxies, hidden in the polarization of quasar light. Each observation is a piece of the puzzle, but we don't yet know what picture they're forming. Will we eventually prove that the universe rotates? Will we discover that the anomalies have a different explanation entirely? Or will this remain one of those tantalizing mysteries that keeps us wondering, keeps us searching, keeps us humble in the face of cosmic complexity? Only time and more observation will tell. But perhaps the answer matters less than the question. The very fact that we can ask whether the universe rotates, that we can search for evidence in light that's older than our planet, that we can contemplate structures larger than anything our ancestors could have imagined. This itself is a kind of miracle. We are the universe becoming aware of itself, contemplating its own nature, wondering about its own properties. In this sense, whether the universe rotates or not, we are all part of a cosmic revolution. The revolution of matter becoming conscious, of atoms arranging themselves into patterns that can think about atoms, of space and time giving rise to beings who can question space and time. This is the deepest rotation of all, the turning of the universe towards self-awareness, the slow spin of cosmic evolution that has brought us to this moment of wonder. As we prepare to explore even deeper into this mystery, to examine the theoretical frameworks and speculative possibilities that might explain a rotating universe, remember that we're not just passive observers of this cosmic dance. We're participants, made of the same stuff as the stars, governed by the same laws, part of the same vast turning, whether literal or metaphorical, that encompasses all of existence. The night continues to unfold around us, filled with questions that have no easy answers, with mysteries that may take generations to solve, with wonders that exceed our capacity to fully comprehend. And in that unfolding, in that questioning, in that wonder, we find our place in the cosmos, not as outside observers but as inside participants in the greatest story ever told, the story of a universe coming to know itself, one observation, one theory, one sleepless night of contemplation at a time. The evidence for cosmic rotation doesn't rest solely on the cosmic microwave background, though that ancient light provides our most tantalizing clues. As we venture deeper into this mystery tonight, we find ourselves examining an entire constellation of observations, each offering its own whisper of something profound. Scientists have observed patterns in the oldest light, yes, but also in the distribution of galaxies, in the polarization of distant quasars, and in subtle asymmetries that shouldn't exist if our universe were perfectly uniform in all directions. Let me share with you what we've found, not with the certainty of proclamation, but with the gentle curiosity of exploration. When scientists first analysed the cosmic microwave background in detail, they were looking for confirmation of our standard cosmological model. This model, sometimes called lambda CDM, describes a universe that began with a big bang, inflated rapidly in its first fraction of a second, and has been expanding ever since, with that expansion accelerating due to dark energy. The model predicts that on the largest scales the universe should be homogeneous and isotropic, the same everywhere and in all directions. The CMB should reflect this, showing random temperature variations with no preferred orientation or special direction. But data from COBE and later from WMAP and Planck revealed something unexpected. The temperature fluctuations in the CMB, when broken down into their fundamental components, using a mathematical technique called spherical harmonic analysis, showed peculiar alignments. Think of this analysis as being like decomposing music into its individual notes and harmonies. Just as a song might have a dominant key or rhythm, the CMB seems to have dominant orientations, particularly in its lowest harmonics. The quadrupole component, which represents the simplest possible pattern of hot and cold spots across the sky, appears to be aligned with the ecliptic plane, the plane in which Earth orbits the Sun. At first, this seemed like it must be a systematic error, some contamination from our solar system affecting the measurements. But when scientists looked at the octopole, the next level of complexity, they found it too was aligned, both with the quadrupole and with the ecliptic. The probability of this happening by chance is extremely small, less than 1 in 1,000 according to some analyses. Even more intriguingly, when cosmologists looked at the entire southern hemisphere of the CMB sky versus the northern hemisphere, they found an asymmetry. The southern hemisphere shows slightly less variation in temperature than the northern hemisphere. It's as if the universe is quieter, more uniform, in one direction than another. This hemispheric asymmetry has been confirmed by all 3 major CMB satellites, making it difficult to dismiss as an instrumental artifact. Data suggests something else remarkable as well. There appears to be a lack of correlation in temperature fluctuations at angles greater than about 60 degrees. In the standard model, we would expect correlations at all angles, with the strength decreasing gradually with separation. But observations show a sharp cutoff, as if the universe has a maximum scale of correlation, a largest possible pattern size. Some theorists have suggested this could be evidence that our observable universe is all there is, that space is finite rather than infinite, but the interpretation remains controversial. Perhaps most mysteriously, there's what's known as the CMB cold spot, a region in the constellation Eridanus where the temperature is significantly lower than expected. This cold spot is about 10 degrees across, far larger than typical CMB fluctuations, and its existence is difficult to explain within the standard model. Some scientists have proposed it could be evidence of a collision between our universe and another bubble universe in an eternal inflation scenario, though this remains highly speculative. Now imagine these various anomalies not as separate puzzles, but as pieces of a single picture we don't yet fully see. The alignments, the asymmetries, the cold spot. What if they're all manifestations of the same underlying phenomenon? What if they're all telling us that our universe has a preferred direction, a cosmic axis around which everything else is organized? This brings us to the polarization of the CMB, another layer of information encoded in this ancient light. When light scatters off electrons, it becomes polarized, vibrating preferentially in certain directions. The CMB is weakly polarized, and this polarization contains information about the universe when the CMB was released. Scientists have found that the polarization patterns also show unexpected features, including possible alignments with the temperature anomalies. Even more intriguingly, some analyses have found evidence for what's called parity violation in the CMB polarization. In physics, parity is a symmetry that says the laws of physics should be the same if you flip everything as in a mirror. Most fundamental forces respect parity, but some don't. If the CMB shows parity violation, it could indicate new physics beyond our standard models, possibly related to the universe's rotation or to exotic fields present in the early universe. The search for cosmic rotation extends to the universe's larger structures. Galaxies aren't distributed randomly through space, but form a vast cosmic web of filaments and voids. The filaments, where galaxies cluster, seem to have preferred orientations in some regions of the sky. Some studies have found that these orientations correlate with the CMB anomalies, suggesting a connection between the universe's largest and oldest features. When we look at spiral galaxies specifically, we can classify them as left-handed or right-handed based on the direction their arms appear to wind. In an isotropic universe with no preferred direction, we should see equal numbers of each type regardless of where we look. But some surveys have reported an excess of left-handed galaxies in one direction and right-handed galaxies in the opposite direction, exactly what we'd expect if the universe were rotating. The data reveals these asymmetries most clearly when we look at galaxies at intermediate distances, neither too close nor too far away. This makes sense if we think about it. Nearby galaxies are dominated by local gravitational effects, while very distant galaxies are too faint for us to reliably determine their handedness. It's in that sweet spot, galaxies between about 500 million and 2 billion light-years away, where the cosmic signal might be strongest. Scientists have also examined the orientation of galaxy clusters, the largest gravitationally bound structures in the universe. These massive collections of hundreds or thousands of galaxies seem to have preferred alignments along what some researchers call cosmic highways, filaments of the cosmic web. More surprisingly, some studies suggest these alignments extend over billions of light-years, far larger than expected from gravitational effects alone. The polarization of light from quasars provides another line of evidence. Quasars are among the brightest objects in the universe, powered by matter falling into supermassive black holes. Their light is often polarized, and the angle of this polarization should be random if the universe has no preferred direction. But observations suggest otherwise. Studies of hundreds of quasars have found that their polarization angles are correlated over vast distances, sometimes billions of light-years. This correlation is particularly strong along certain axes that, intriguingly, seem related to the CMB anomalies. It's as if the quasars are responding to the same cosmic organization that creates the CMB alignments. The effect is subtle, requiring statistical analysis of many quasars to detect, but it's persistent across different surveys and different research groups. Recently, scientists have been investigating cosmic birefringence, a phenomenon predicted by certain theories beyond the standard model of particle physics. Birefringence is what happens when different polarizations of light travel at slightly different speeds, causing the polarization angle to rotate as the light propagates. We see this effect in certain crystals on Earth, but it could also happen in the vacuum of space if certain exotic particles or fields are present. Observations suggest that the CMB polarization may indeed show cosmic birefringence. The effect is tiny, a rotation of only about 0.3 degrees, but if real, it would be revolutionary. It would mean that space itself has a kind of handedness, treating left and right differently. This could be related to universal rotation, or it could indicate the presence of axion-like particles, hypothetical particles that could make up dark matter. The evidence from radio galaxies adds another layer to our mystery. Radio galaxies are galaxies with powerful jets of particles shooting out from their central black holes. These jets emit radio waves that we can detect from Earth. The orientation of these jets should be random, but some studies have found preferred alignments, particularly when looking at large samples of distant radio galaxies. Data from radio surveys reveals that these alignments seem to follow a dipole pattern across the sky, an excess in one direction and a deficit in the opposite direction. This is exactly what we'd expect if the universe were rotating, with the rotation axis defining the special direction. The signal is weak and controversial, with different studies reaching different conclusions, but it adds to the accumulating evidence for cosmic anisotropy. Even the cosmic ray particles that constantly bombard Earth may carry information about universal rotation. Ultra-high energy cosmic rays, particles with energies millions of times greater than what we can produce in our most powerful accelerators, seem to arrive preferentially from certain directions. While this could be due to the distribution of nearby sources, some researchers have suggested it might reflect a deeper cosmic asymmetry. Observations of type Ia supernovae, the standard candles that astronomers use to measure cosmic distances, have also revealed potential anomalies. These exploding stars should be distributed uniformly across the sky, but some analyses suggest there are directional variations in their properties. The supernovae in one direction might be slightly brighter or dimmer than those in another direction, possibly indicating that the universe's expansion rate varies with direction. The integrated Sachs-Wolf effect provides yet another probe of cosmic structure. This effect occurs when CMB photons gain or lose energy as they pass through the gravitational wells of large structures. By correlating CMB temperature with galaxy surveys, scientists can map this effect. Some studies have found that the correlation is stronger in certain directions, again suggesting a cosmic preferred axis. When we consider dark matter, that mysterious substance that makes up most of the matter in the universe, we find more hints of cosmic rotation. The distribution of dark matter, inferred from gravitational lensing and galaxy motions, seems to show large-scale flows and alignments that weren't predicted by standard models. These dark flows could be the result of structures beyond our observable universe, or they could be manifestations of universal rotation. Scientists have found that even the fine structure constant, one of the fundamental constants of nature that determines the strength of electromagnetic interactions, might vary across the sky. Observations of distant quasars suggest the constant might be slightly different in different directions, though this remains highly controversial. If confirmed, it would suggest that the laws of physics themselves might have a directional dependence, a profound challenge to our understanding of nature. The evidence from gravitational lensing adds another dimension to our investigation. When light from distant galaxies passes near massive objects, its path is bent by gravity, creating distorted or multiple images. The pattern of these distortions should be random, but some studies suggest there are preferred orientations, particularly for the most massive lensing clusters. These orientations seem to correlate with other cosmic anomalies, adding another thread to our tapestry of evidence. Data reveals that even the cosmic neutrino background, the sea of neutrinos left over from the Big Bang, might carry information about universal rotation. While we can't detect these relic neutrinos directly with current technology, their gravitational effects on other matter could create observable signatures. Some theoretical calculations suggest that universal rotation would create a characteristic pattern in the neutrino distribution that might be detectable with future observations. As we compile all this evidence, a picture begins to emerge, not a clear, definitive image, but more like an impressionist painting where individual brushstrokes suggest a larger pattern. No single observation proves that the universe is rotating. Each piece of evidence has alternative explanations, systematic uncertainties, debates about statistical significance, but taken together, they create an intriguing case for cosmic anisotropy, for the possibility that our universe has a preferred direction. The axis that emerges from these various observations doesn't point in exactly the same direction for each phenomenon. The CMB anomalies suggest an axis roughly toward Virgo. The quasar polarizations point toward a slightly different direction. The galaxy alignments indicate yet another orientation. This could mean that different phenomena are sensitive to different aspects of cosmic anisotropy, or it could indicate that we're seeing a combination of real effects and systematic errors. It's also worth noting that many of these anomalies are at the edge of statistical significance. They're not the clear, unambiguous signals we might hope for, but rather subtle hints that require careful analysis to tease out. This is perhaps not surprising given the magnitude of what we're looking for. A rotation so slow that the universe would take trillions of years to complete even a fraction of a turn. The challenge of detecting universal rotation is compounded by our position within the universe. We're like sailors trying to determine if the ocean is rotating by studying the waves around our ship. We can't step outside to get an objective view. We can only look for subtle clues in the patterns of waves, the direction of currents, the alignment of distant landmarks, and we have to do all this while our ship is also moving, adding its own motion to everything we observe. This is why the search for cosmic rotation requires such diverse lines of evidence. No single observation can prove or disprove it. We need to look at the universe from every angle, with every tool at our disposal, searching for consistent patterns that transcend individual measurements. It's a detective story, where the crime scene is the entire observable universe, and the evidence has been travelling toward us for billions of years. As technology improves, our ability to detect these subtle signals increases. The next generation of telescopes and satellites will provide unprecedented precision in measuring the CMB, mapping galaxy distributions, and detecting polarization. The square-kilometre array will survey millions of radio galaxies. The Vera Rubin Observatory will map billions of optical galaxies. The European Space Agency's Euclid mission will trace the cosmic web in 3 dimensions. Each of these projects has the potential to either confirm or refute the evidence for cosmic rotation. But perhaps the most exciting possibility is that we'll discover something entirely unexpected. History shows that when we push our observations to new frontiers, we often find phenomena we didn't predict. Dark matter and dark energy were both discovered this way. The accelerating expansion of the universe came as a complete surprise. Perhaps the hints of cosmic rotation are pointing us toward another revolutionary discovery, something that will once again transform our understanding of the cosmos. For now, though, we live with uncertainty, with tantalizing hints rather than definitive answers. The universe might be rotating around an invisible axis, or it might not. The anomalies we observe might be profound clues about the nature of reality, or they might be subtle systematic effects we haven't properly accounted for. This uncertainty isn't a weakness of science, but its strength. The willingness to follow the evidence wherever it leads, to remain open to possibilities while demanding rigorous proof. As you lie there in the darkness, perhaps you can feel yourself part of this cosmic investigation. Your consciousness, a small but essential part of the universe's attempt to understand itself. Every question we ask, every observation we make, every theory we propose is the cosmos examining its own nature through us. We are the universe's way of looking at itself in the mirror, searching for asymmetries, patterns, and meanings in its own reflection. The radio waves from distant galaxies that reveal potential alignments have been travelling through space since before our solar system formed. The polarized light from quasars that hints at cosmic organization left its source when the universe was young and wild. The cosmic microwave background that shows those mysterious patterns is older still, a fossil from the universe's infancy. All these signals converge here and now, in our telescopes and detectors, in our computers and equations, in our minds as we try to piece together the grand puzzle of existence. Consider the profound patience this requires. Astronomers spend entire careers studying signals that have been travelling through space for longer than life has existed on Earth. They analyse data with statistical techniques that can take months to run on supercomputers. They debate interpretations in conferences and journals, slowly building consensus or disagreement over years and decades. It's a multi-generational conversation with the cosmos, each scientist adding their small contribution to humanity's growing understanding. And what if we never find definitive proof one way or the other? What if the universe's rotation, or lack thereof, remains forever just beyond our ability to measure with certainty? Even then, the search will have been worthwhile. It will have pushed us to develop new technologies, new mathematical techniques, new ways of thinking about space and time. It will have revealed other phenomena we weren't looking for. It will have deepened our appreciation for the subtlety and complexity of the cosmos. The possibility of universal rotation also reminds us that our everyday experience provides poor intuition for the universe at large. We live in a world where up and down seem absolute, where rotation is always relative to something else, where space appears flat and time flows uniformly. But the universe operates on scales and principles far removed from our daily experience. What seems impossible or paradoxical to us might be perfectly natural on a cosmic scale. This is perhaps the deepest lesson of modern cosmology. The universe is not obligated to conform to our expectations. It's far stranger, far more wonderful, and far more mysterious than our ancestors could have imagined. And if it's rotating around an invisible axis, that's just one more reminder of how much we still have to learn. How many surprises still await us in the cosmic dark? As we prepare to delve into the speculative frameworks that might explain a rotating universe, remember that we're venturing into territory where observation meets imagination, where data confronts theory, where the known borders the unknown. The evidence we've examined, the CMB anomalies, the galaxy alignments, the quasar polarizations, these are the observational anchors for our theoretical flights. Now we must ask, if the universe is rotating, what could cause such rotation? What mechanisms, what principles, what cosmic processes could set the entire universe spinning? The answer to these questions will take us deep into theoretical physics, into models of the early universe, into speculations about extra dimensions and cosmic topology. We'll explore ideas that push the boundaries of science, that challenge our fundamental assumptions about reality. Some of these ideas might seem like science fiction, but remember that yesterday's science fiction often becomes today's science fact. The Big Bang itself once seemed absurd. The expansion of the universe was initially rejected by Einstein himself. Dark energy was completely unexpected. Perhaps universal rotation will join this list of cosmic surprises that eventually became accepted science. Now we turn to the theoretical tapestry, where physicists and cosmologists have woven various frameworks attempting to explain how and why our universe might possess this grand rotation. Consider the possibility that the seeds of cosmic rotation were planted in the universe's first moments, in that brief epoch of cosmic inflation when space itself expanded faster than light. Scientists have proposed models where inflation wasn't perfectly uniform, where quantum fluctuations or initial conditions created a slight twist in the fabric of space-time itself. These models, with names like vector inflation and anisotropic inflation, suggest that the universe could have been born with a preferred direction already encoded in its very structure. What if, just maybe, the inflation field, that hypothetical field that drove the universe's rapid early expansion, had a directional component? Picture it like this. Instead of inflating uniformly like a perfectly spherical balloon, the universe expanded with a subtle bias, perhaps stretching slightly more in one direction, or expanding with a gentle helical twist. The mathematics of these models is formidable, involving tensor equations and gauge theories that push even theoretical physicists to their limits. But the basic idea is beautifully simple. If the universe's expansion had any directional preference in its first fraction of a second, that preference would be preserved and amplified as the universe grew, eventually manifesting as the large-scale alignments we observe today. Some theorists have proposed that our universe might be described by what are called Bianchi models, named after the Italian mathematician Luigi Bianchi, who classified all possible three-dimensional geometries. Unlike the standard Friedmann-Lemaitre-Robertson-Walker models that assume the universe is homogeneous and isotropic, Bianchi models allow for universes that expand at different rates in different directions. Imagine space itself having a grain, like wood, with natural directions along which the universe prefers to expand. In certain Bianchi models, this anisotropic expansion can create effects that mimic rotation, even if the universe isn't actually spinning in the conventional sense. The mathematics reveals 9 different types of Bianchi universes, each with its own peculiar geometry and expansion history. Type 1 is the simplest, with different expansion rates along 3 perpendicular axes. Type 9 is the most complex, with a geometry that naturally incorporates rotation. Some of these models predict that the universe should become more isotropic over time, with the initial anisotropy fading away. But others suggest that anisotropy could persist or even grow under certain conditions. The CMB anomalies might be fossil remnants of our universe's Bianchi heritage, preserved in the oldest light we can see. Perhaps even more intriguingly, some physicists have suggested that our universe might have inherited its rotation from whatever came before the Big Bang. In eternal inflation models, our universe is just one bubble in an infinite multiverse, constantly spawning new universes through quantum fluctuations. If the parent universe, or the quantum fluctuation that created our universe, had angular momentum, that rotation could be passed on to our cosmic bubble. It's like a cosmic heredity, with physical properties transmitted from parent universe to child universe across the boundary of the Big Bang. Consider the possibility that the universe's topology, its overall shape and connectivity, might create the illusion of rotation. We usually assume the universe is simply connected, meaning it has no holes or handles, like the surface of a sphere. But what if the universe is multiply connected, like the surface of a torus, a donut shape, or something even more exotic? In such universes, light could travel multiple paths to reach us, and the interference between these paths could create patterns that mimic the effects of rotation. Scientists have proposed models where the universe is finite but unbounded, wrapping around on itself in complex ways. In these models, we might be seeing the same distant structures from multiple directions, like being in a hall of mirrors where the reflections create patterns that aren't really there. The CMB anomalies could be interference patterns created by this cosmic hall of mirrors effect. Some topologies naturally create preferred directions. For instance, a toroidal universe has a long way around and a short way around, automatically breaking isotropy. The idea of extra dimensions adds another layer of possibility to our mystery. String theory and other attempts at quantum gravity suggest that our universe might have more than the 3 spatial dimensions we experience. These extra dimensions are usually assumed to be compact, curled up so small we can't detect them directly. But what if these extra dimensions have their own dynamics? What if they're rotating or processing in ways that affect our 3-dimensional space? Imagine our 3-dimensional universe as a membrane, or brain, floating in a higher dimensional space. If this brain is rotating in the extra dimensions, we would experience effects that look like rotation within our 3-dimensional world, even though the actual rotation is happening in dimensions we can't directly perceive. It's like the shadow of a rotating 4-dimensional object, creating patterns in 3 dimensions that seem mysterious until you understand the higher dimensional origin. Models with names like Kaluza-Klein theory and Randall-Sundrum scenarios explore these possibilities. In some versions, the extra dimensions could be large, perhaps even infinite, with gravity being the only force that can propagate through them. The rotation of our brain through these large extra dimensions could create the cosmic axis we observe, with the direction of the axis determined by the orientation of our brain in the higher dimensional space. Now imagine that dark energy, that mysterious force causing the universe's expansion to accelerate, might be related to cosmic rotation. Some theorists have proposed that what we interpret as dark energy might actually be the centrifugal effect of the universe's rotation. Just as spinning makes things want to fly outward, cosmic rotation could create an apparent outward force that we mistake for dark energy. The mathematics of this is subtle, involving the interplay between rotation and the curved space-time of general relativity, but it offers a tantalizing possibility. 2 of cosmology's greatest mysteries, dark energy and the CMB anomalies, might have a single explanation. Quantum mechanics might also play a role in cosmic rotation. In quantum field theory, empty space isn't really empty but filled with quantum fluctuations, particles and antiparticles constantly appearing and disappearing. These quantum fluctuations could have a preferred handedness or chirality, especially if the laws of physics violate certain symmetries. This quantum handedness could accumulate over cosmic scales, creating a universal preference for rotation in one direction over another. Consider the fascinating possibility that the universe might be rotating because of something called torsion. In Einstein's general relativity, space-time can be curved by matter and energy, but it's assumed to have no torsion, no intrinsic twist. But some extensions of general relativity, like Einstein-Cartan theory, allow space-time to have torsion as well as curvature. In these theories, the spin of elementary particles can generate torsion, and this torsion can accumulate to create large-scale rotation. The presence of torsion would modify many of our cosmological calculations. It would affect how the universe expanded in its early moments, how structures formed, how light propagates through space. Some scientists have suggested that torsion could eliminate the initial singularity of the Big Bang, replacing it with a big bounce, where a previous universe contracted down to a minimum size before expanding again. The rotation we observe could be a remnant from this previous cosmic cycle, angular momentum that survived the bounce. Data suggests another intriguing possibility. The universe might be rotating because it's entangled with something else. In quantum mechanics, particles can be entangled, sharing a quantum state even when separated by vast distances. Some theorists have speculated that our entire universe might be entangled with another universe, or with structures beyond our cosmic horizon. This entanglement could create correlations that manifest as the large-scale alignments we observe. Perhaps the universe's rotation is related to the mysterious dark matter that makes up most of the matter in the cosmos. What if dark matter particles have properties that create a preferred direction in space? For instance, if dark matter consists of axions, hypothetical particles that could solve several problems in physics, these particles could create a cosmic axion field with a preferred orientation. This field could interact with ordinary matter and radiation in ways that produce the observed CMB anomalies and galaxy alignments. Some scientists have proposed that the universe might be inside a black hole, and the rotation we observe is inherited from the black hole's spin. In this scenario, what we call the Big Bang was actually the formation of the black hole, and our expanding universe is the interior of this cosmic black hole continuing to evolve. The mathematics of black hole interiors in general relativity is notoriously complex, but some solutions do suggest that rotating black holes could have interior regions that look like expanding universes with preferred directions. The holographic principle offers yet another framework for understanding cosmic rotation. This principle, inspired by black hole physics and string theory, suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. If our universe is holographic, the three-dimensional space we experience might be a projection from a two-dimensional boundary. Rotation in this boundary theory could manifest as the cosmic alignments and asymmetries we observe in 3 dimensions. Consider this. The universe might be rotating not through space but through time. In relativity, space and time are unified into space-time, and rotations can mix spatial and temporal coordinates. A universe with temporal rotation would have a preferred direction in space-time which could manifest as the spatial alignments we observe. This is a mind-bending concept that challenges our intuitive notions of time and rotation, but it's mathematically consistent within the framework of general relativity. Scientists have also explored the possibility that the universe's apparent rotation might be caused by our motion through a larger structure. If our observable universe is moving through a larger cosmos, this motion could create apparent alignments and asymmetries. It's like looking out the window of a moving train. The landscape seems to have a preferred direction of motion, even though it's actually stationary. This tilted universe model suggests that what we interpret as cosmic rotation might actually be cosmic translation. The anthropic principle provides a different perspective on cosmic rotation. This principle notes that we can only observe universes compatible with our existence. Perhaps universes without rotation, or with too much rotation, wouldn't form galaxies, stars, and planets capable of supporting life. We find ourselves in a universe with just the right amount of rotation because that's the only kind of universe where observers like us could exist. It's not a satisfying explanation for many scientists, but it's a logical possibility that can't be dismissed. Some theorists have suggested that cosmic rotation might be related to the arrow of time, the fact that time seems to flow in one direction from past to future. In a rotating universe, the rotation defines a cosmic handedness that could be connected to time's arrow. Perhaps the universe rotates because time flows forward, or time flows forward because the universe rotates. This deep connection between rotation and time's arrow remains speculative, but it hints at profound links between different aspects of cosmic structure. What if the universe's rotation is not constant but changing over time? Some models suggest that the universe might have been rotating faster in the past and is gradually slowing down, like a cosmic flywheel losing energy. Or perhaps the rotation is accelerating, driven by dark energy or some other cosmic force. The CMB gives us a snapshot of the universe's rotation 13.8 billion years ago, while galaxy surveys probe more recent epochs. By comparing these different observations, we might be able to trace the history of cosmic rotation. The possibility of varying rotation leads to another intriguing idea. Perhaps different regions of the universe rotate at different rates or in different directions. The observable universe might be just one rotating domain in a vast cosmos filled with domains rotating every which way, separated by domain walls where the rotation changes. We happen to live in one particular domain, seeing its particular rotation, unaware of the different rotations beyond our cosmic horizon. Quantum cosmology, which attempts to apply quantum mechanics to the universe as a whole, offers additional perspectives on cosmic rotation. In quantum mechanics, angular momentum is quantized. It comes in discrete units. If the universe as a whole is a quantum system, its rotation might be quantized too. This could explain why the rotation is so small. The universe might be in the lowest possible rotation state above zero, rotating at the minimum rate allowed by quantum mechanics. Consider the role of cosmic strings, hypothetical one-dimensional defects in space-time that might have formed in the early universe. If cosmic strings exist, they could act like cosmic flywheels, storing angular momentum and creating preferred directions in space. A network of cosmic strings throughout the universe could generate the large-scale alignments we observe, with the strings acting like invisible scaffolding that organizes cosmic structure. Some scientists have proposed that the universe's apparent rotation might be caused by modifications to gravity on cosmic scales. While general relativity has been tested extensively in the solar system and in binary pulsars, its behavior on cosmological scales is less certain. Modified gravity theories like EMOND, modified Newtonian dynamics, or TeVS, tensor vector scalar gravity, could create effects that mimic rotation without the universe actually spinning. The interplay between electromagnetic fields and gravity provides another avenue for cosmic rotation. In some theories, the universe might have a primordial magnetic field created in the Big Bang or shortly after. This magnetic field could interact with the universe's expansion to create helical patterns and preferred directions. The rotation of charged particles in this cosmic magnetic field could generate the polarization patterns we observe in the CMB and in distant quasars. Perhaps the universe's rotation is related to the fundamental constants of nature. If constants like the fine structure constant, or the ratio of the proton to electron mass vary slightly across the universe, this variation could create apparent alignments and asymmetries. Some observations of distant quasars hint at such variation, though the evidence remains controversial. A universe with varying constants would be profoundly different from the one described by our standard models, requiring new physics to understand. As we contemplate these various theoretical frameworks, it's important to remember that they're not mutually exclusive. The universe's rotation, if it exists, might result from a combination of effects. Perhaps there's some primordial rotation from inflation, enhanced by the universe's topology, modified by quantum effects, and observed through the lens of our particular motion through the cosmos. The truth might be more complex and more beautiful than any single theory suggests. The challenge for theorists is to make specific, testable predictions. It's not enough to show that a theory could produce cosmic rotation. It must predict specific observational signatures that distinguish it from other theories. For instance, different models predict different relationships between the CMB anomalies and galaxy alignments, different patterns of polarization, different evolution over cosmic time. As our observations become more precise, we can rule out some theories and refine others. The next generation of observations will be crucial for testing these theoretical ideas. The Simons Observatory and CMB-S4 will map the cosmic microwave background with unprecedented precision. The Square Kilometre Array will survey millions of galaxies, tracing cosmic structure in exquisite detail. The Laser Interferometer Space Antenna, LISA, will detect gravitational waves from the early universe, potentially carrying information about primordial rotation. Each of these projects offers the possibility of discovering the smoking gun that proves or disproves cosmic rotation. But perhaps the most exciting possibility is that observations will reveal something none of our current theories predict. History shows that nature is often more imaginative than human theorists. The discovery of dark energy came as a complete surprise. The cosmic web's complexity exceeded all expectations. If the universe is rotating, the true explanation might involve physics we haven't yet imagined, principles we haven't yet discovered. For now, we exist in a state of creative tension between observation and theory, between what we see and what we understand. The universe might be rotating around an invisible axis, driven by exotic physics and primordial conditions we're only beginning to glimpse. Or the apparent rotation might be an illusion, a combination of systematic effects and statistical flukes that will disappear with better data. Either possibility is profound, one reshaping our understanding of the cosmos, the other reminding us of the subtle challenges in reading the universe's messages. As you drift deeper into the night, perhaps you can feel yourself part of this theoretical adventure, your imagination joining the collective human effort to understand our cosmic home. Every equation written, every model proposed, every simulation run is humanity reaching toward truth, using mathematics and physics as languages to decode the universe's deepest secrets. We may not have the answers yet, but we have something equally valuable: the questions and the tools to pursue them. The theoretical landscape of cosmic rotation is vast and varied, filled with peaks of possibility and valleys of uncertainty. We traverse this landscape not with certainty but with curiosity, not with dogma but with openness to wherever the evidence leads. And in this traversal, in this exploration of possible universes and potential physics, we discover not just facts about the cosmos but truths about ourselves, our capacity for wonder, our persistence in the face of mystery, our deep desire to understand our place in the grand scheme of existence. Now we turn our attention to the remarkable fleet of instruments humanity has deployed to listen to the cosmos's whispers, each mission adding its voice to our growing chorus of cosmic observation. Picture, if you will, a vast network of mechanical eyes turned skyward, each designed to capture different wavelengths of light, different messengers from the depths of space and time. These missions, past, present, and future, form humanity's sensory extension into the cosmos, allowing us to perceive what our biological eyes never could. The story of our search for cosmic rotation through instrumentation begins with COBE, the Cosmic Background Explorer, launched in 1989. COBE was like a pioneer setting out into unexplored territory, carrying instruments that would fundamentally change our view of the universe. Its far-infrared absolute spectrophotometer confirmed that the CMB had exactly the black-body spectrum predicted by the Big Bang theory. But more importantly for our story, its differential microwave radiometer detected those tiny temperature variations in the CMB, the seeds of all cosmic structure. When the team presented their first full-sky map showing those primordial hot and cold spots, they received a standing ovation from their scientific colleagues. It was like seeing the universe's baby picture for the first time. COBE's map was revolutionary but crude by today's standards, with angular resolution of about 7 degrees, roughly 14 times the width of the full moon. Scientists knew that to understand the universe's structure and test our cosmological models, we needed to see finer details. This led to WMAP, the Wilkinson Microwave Anisotropy Probe, named after cosmologist David Wilkinson. Launched in 2001, WMAP was positioned at the L2 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, where the spacecraft could observe the entire sky without interference from Earth or the Sun. WMAP's refined lullaby of data transformed cosmology from a field of rough estimates to a precision science. Its measurements were so precise that we could determine the universe's age to within 1%, 13.77 billion years. It mapped the CMB with 45 times better resolution than COBE, revealing not just the primary temperature fluctuations but also the polarization of the CMB light. And it was WMAP that first clearly showed those troubling alignments, those large-scale patterns that seemed to pick out special directions in space. The quadrupole and octopole modes weren't randomly oriented as expected, but seemed to align with each other and, puzzlingly, with our solar system's orbital plane. Scientists have found that WMAP operated for 9 years, far exceeding its planned 2-year mission. During this time, it scanned the entire sky every 6 months, building up an increasingly detailed and noise-free map of the cosmic microwave background. Each scan added to our understanding, like an artist adding layers to a painting, gradually revealing subtle features that weren't visible in earlier, noisier maps. The mission produced a treasure trove of data that cosmologists are still analysing today, finding new patterns and testing new theories against WMAP's precise measurements. Then came Planck, the European Space Agency's ambitious CMB mission, launched in 2009. If COBE was the pioneer and WMAP the surveyor, Planck was the master cartographer, creating the most detailed map of the ancient universe we've ever had. With instruments cooled to just 1/10 of a degree above absolute zero, Planck could detect temperature variations as small as a few millionths of a degree. Its angular resolution was about 5 arc-minutes, allowing it to see structures in the CMB that WMAP couldn't resolve. Planck's detailed tapestry of observations confirmed many of WMAP's findings, including those mysterious alignments. But it also revealed new anomalies. The hemispheric asymmetry became clearer. One half of the sky really does seem to have different statistical properties than the other. The cold spot in Eridanus was confirmed and studied in detail, and Planck's polarization measurements added a new dimension to our understanding, showing that the polarization patterns also have unexpected features that might be related to cosmic rotation. Data reveals that Planck observed in 9 frequency bands, from 30 to 857 GHz, allowing it to separate the CMB signal from foreground contamination with unprecedented accuracy. This multi-frequency approach was crucial because our galaxy emits radiation that can mask the CMB signal. Dust grains in our galaxy emit infrared radiation. Free electrons create synchrotron radiation. These foregrounds have to be carefully modelled and removed to reveal the pure CMB signal underneath. It's like trying to hear a whisper in a noisy room. You need to identify and filter out all the other sounds. But our search for cosmic rotation extends far beyond the CMB. Enter Gaia, the European Space Agency's star mapping satellite, creating a 3-dimensional map of our galaxy with unprecedented precision. Launched in 2013, Gaia measures the positions, distances, and motions of nearly 2 billion stars. While its primary mission focuses on our galaxy, Gaia also observes millions of quasars, those distant lighthouses that might reveal cosmic rotation through their orientations and polarizations. Gaia's contribution to our story comes through its incredible precision. It can measure positions to an accuracy of a few millionths of an arc-second, equivalent to measuring the width of a human hair from 1,000 kilometers away. This precision allows it to detect tiny systematic effects that might be caused by cosmic rotation. If the universe is rotating, it should create a subtle pattern in how distant objects appear to move across the sky, and Gaia has the sensitivity to detect such patterns. Now imagine Euclid, another ESA mission that launched in 2023, designed to map the geometry of the dark universe. Euclid observes billions of galaxies, measuring their shapes and distributions to understand dark matter and dark energy. But these observations also provide data on galaxy orientations and alignments that could reveal cosmic rotation. Euclid's wide-field camera can image an area of sky equivalent to 2 full moons in a single exposure, allowing it to survey large portions of the sky efficiently. The James Webb Space Telescope, though primarily designed for other purposes, contributes to our search as well. JWST's incredible infrared sensitivity allows it to see the universe's first galaxies, observing how they formed and evolved. If the universe has a preferred axis, it might affect how these early galaxies formed, their orientations, their clustering patterns. JWST's observations of these ancient embers of light provide a window into the universe when it was only a few 100 million years old, potentially revealing how cosmic rotation, if it exists, affected structure formation. Scientists have deployed ground-based telescopes as well, each adding unique capabilities to our cosmic census. The Atacama Cosmology telescope in Chile's high desert observes the CMB from Earth, achieving resolution comparable to space-based missions for small patches of sky. The South Pole telescope, taking advantage of the dry, stable atmosphere at Earth's bottom, has mapped the CMB temperature and polarization with exquisite detail. These ground-based observatories can be upgraded with new instruments as technology advances, something impossible with space missions. The Sloan Digital Sky Survey has created the most detailed 3-dimensional maps of the universe, cataloguing millions of galaxies and quasars. Its data has been crucial for studying large-scale structure and searching for cosmic alignments. The survey's spectroscopic observations reveal not just where galaxies are, but how fast they're moving, potentially revealing the flows and rotations that might indicate universal spin. Looking to the future, the Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will conduct the Legacy Survey of Space and Time. This remarkable instrument will photograph the entire visible sky every few nights, tracking how the universe changes over time. With its 3.2 gigapixel camera, the largest digital camera ever built, it will catalogue billions of galaxies, providing an unprecedented dataset for studying cosmic structure and searching for signs of universal rotation. The square-kilometre array represents perhaps our most ambitious ground-based project. When complete, it will be the world's largest radio telescope, with collecting area of approximately 1 square kilometre, spread across thousands of individual antennas. The SKA will observe millions of galaxies in radio wavelengths, measuring their distributions and orientations with unprecedented precision. Its sensitivity will allow it to detect the faint radio whispers from galaxies billions of light-years away, potentially revealing cosmic alignments invisible to optical telescopes. Data suggests the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky efficiently. Roman will study dark energy through multiple techniques, including observations of Type Ia supernovae and gravitational lensing. These observations could reveal whether the universe's expansion rate varies with direction, a potential signature of cosmic rotation. The Laser Interferometer Space Antenna, or LISA, will open an entirely new window on the universe by detecting gravitational waves from space. These ripples in space-time, predicted by Einstein and first detected by LIGO in 2015, carry information about the universe's most violent events. LISA will be sensitive to much lower frequency gravitational waves than ground-based detectors, potentially including waves from the early universe that could carry information about primordial rotation. Imagine 3 spacecraft separated by millions of kilometers, forming a vast triangle in space. Laser beams connect them, measuring the distance between spacecraft to incredible precision. When a gravitational wave passes through, it stretches and squeezes space itself, changing these distances by amounts smaller than the width of an atom. Yet LISA will detect these minute changes, reading the gravitational symphony of the cosmos. Scientists have proposed even more ambitious missions for the future. The Primordial Inflation Explorer, PIXI, would measure the CMB spectrum to extraordinary precision, potentially detecting the faint signatures of cosmic inflation or rotation. The Cosmic Origins Explorer, CORE, would map CMB polarization with sensitivity far exceeding current missions. These future missions remain in the proposal stage, awaiting funding and technological development, but they represent humanity's continued commitment to understanding our cosmic home. Each mission operates in its own unique way, with instruments designed for specific observations. Some use bolometers, devices that measure the energy of incoming radiation by detecting the tiny temperature increase it causes. Others use radiometers that compare the signal from different parts of the sky. Polarimeters measure the orientation of light waves. Spectrometers spread light into its component wavelengths. Each technique has advantages and limitations, and by combining observations from multiple instruments, we build a more complete picture of the universe. The data from these missions doesn't arrive pre-packaged with answers. It requires sophisticated analysis, complex statistical techniques, and careful consideration of systematic errors. Scientists must account for everything from the motion of the spacecraft to the effects of cosmic dust, from the instrument's response function to the gravitational lensing by intervening matter. It's like trying to reconstruct a symphony from a recording made in a noisy, echoing hall. You need to understand and remove all the distortions to hear the original music. The computational requirements for analyzing this data are staggering. A single analysis of Planck data might require millions of CPU hours, running on supercomputers for weeks or months. Scientists use techniques like Monte Carlo simulations, generating thousands of simulated universes to understand the statistical significance of observed patterns. They employ Bayesian analysis to compare different models, machine learning to identify patterns, and sophisticated map-making algorithms to convert raw time-ordered data into sky maps. International collaboration is essential for these missions. Planck involved scientists from over 100 institutions worldwide. The SKA includes member countries from 5 continents. These collaborations bring together diverse expertise: physicists who understand the theory, engineers who build the instruments, computer scientists who develop the analysis software, statisticians who assess significance. It's a global effort to understand our cosmic home, transcending national boundaries in pursuit of universal truth. The cost of these missions is substantial but tiny compared to many other human endeavours. JWST, one of the most expensive space telescopes ever built, cost about $10 billion over 2 decades, less than what humanity spends on cosmetics in a single year. The scientific return on these investments is immeasurable. Not just the knowledge gained, but the technologies developed, the students trained, the international cooperation fostered, the inspiration provided to future generations. Ground-based and space-based observations complement each other beautifully. Ground-based telescopes can be larger and can be upgraded with new instruments, but they must peer through Earth's atmosphere, which blocks certain wavelengths and blurs images. Space telescopes are smaller and can't be serviced, with rare exceptions like Hubble, but they have access to the full electromagnetic spectrum and can achieve sharper images. By combining observations from both domains, we get a more complete picture of the universe. The synchronization between different missions creates particularly powerful insights when LIGO detects gravitational waves from colliding neutron stars, optical telescopes swing into action to observe the electromagnetic counterpart. When Planck maps the CMB, galaxy surveys provide the 3-dimensional structure that helps interpret the 2-dimensional CMB patterns. These multi-messenger observations, combining different types of cosmic signals, provide far more information than any single observation could. As technology advances, our ability to detect subtle cosmic signals improves dramatically. The detectors on modern CMB missions are approaching fundamental limits set by quantum mechanics. Future improvements will come from observing longer, covering more sky, or measuring more frequencies. New technologies like kinetic inductance detectors and transition edge sensors push sensitivity to new extremes. Advances in computing allow more sophisticated analyses of ever larger datasets. The search for cosmic rotation exemplifies how modern astronomy works. No single observation provides definitive proof. Instead, we build a case from multiple lines of evidence, each with its own strengths and weaknesses. We look for consistency across different observations, different wavelengths, different cosmic epochs. It's like assembling a jigsaw puzzle, where we don't know what the final picture looks like, and we're not even sure all the pieces are from the same puzzle. This patient accumulation of evidence, this careful cross-checking of results, this gradual refinement of understanding, this is how science progresses. It's not about sudden revelations or dramatic breakthroughs, though those occasionally happen. It's about the slow, steady work of thousands of scientists and engineers, each contributing their piece to humanity's growing understanding of the cosmos. The data from all these missions is typically made public after a proprietary period, allowing scientists worldwide to conduct their own analyses. This open data policy democratizes cosmology, enabling researchers at small institutions to make major discoveries. Some of the most important findings about cosmic anomalies have come from scientists reanalyzing public data with new techniques or different perspectives. As we look to the future, new missions are being planned that will push our observational capabilities even further. The CMB-S4 experiment will deploy hundreds of thousands of superconducting detectors across multiple telescopes, achieving sensitivity limited only by fundamental physics. The square-kilometre array will begin operations in phases, with early science beginning in the late 2020s. LISA is scheduled for launch in the 2030s, opening the gravitational wave window on the early universe. These future missions will either confirm the hints of cosmic rotation we're seeing, or reveal them to be misinterpretations of more mundane effects. Either outcome will be valuable. If rotation is confirmed, it will revolutionize our understanding of the cosmos. If it's ruled out, we'll have learned important lessons about systematic errors and statistical analysis that will improve all future observations. But perhaps most importantly, these missions maintain humanity's conversation with the cosmos. Each observation is a question asked of the universe. What are you? How do you work? What is our place within you? And the universe answers, not in words but in the ancient light of the CMB. in the distribution of galaxies, in the polarization of quasars, in gravitational waves rippling through space itself. The instruments we've built to detect these cosmic whispers are among humanity's greatest achievements. They represent our curiosity made manifest, our wonder given form in silicon and steel, aluminum and gold. They float in space or perch on mountaintops, patiently collecting photons that have travelled for billions of years, transforming these ancient messengers into data, into knowledge, into understanding. As you rest there in the darkness, perhaps you can imagine these sentinels of science, scattered across Earth and space, all working in concert to decode the universe's deepest mysteries. Every photon they detect, every measurement they make, adds another note to the cosmic symphony we're slowly learning to hear. And somewhere in that symphony, perhaps, is the subtle rhythm of cosmic rotation, the universe's slow dance around an axis we're only beginning to perceive. The story these missions tell is still being written. New data arrives daily, new analyses are published weekly, new theories are proposed monthly. We live in a golden age of cosmology, where observations are precise enough to test our most fundamental theories, where new discoveries await in datasets already collected but not yet fully analysed, where the next mission might reveal something that changes everything we thought we knew. This ongoing observation of the cosmos is humanity at its best, curious, persistent, collaborative, reaching beyond our small planet to understand our place in the grand scheme of existence. Whether the universe rotates or not, the search itself ennobles us, connects us to something larger than ourselves, reminds us that we are part of a cosmos far grander and more mysterious than our ancestors could have imagined.